Okay, so I'm going to tell you about a number of things that are being threaded together in a research program going on in my group that have to do with how recent progress in machine learning could be used in science, in particular experimental science, where you may have high quantities of data you can collect in experiments, and you'd like to use machine learning to help you decide what experiments to do, but also how to model that data, for example, using causal models. And I'm going to talk about GFlowNets, which is a new kind of probabilistic modeling approach based on neural nets that we've been working on that may help us on both of these fronts. In other words, the modeling side and the experimental design side. Okay. Sorry, I need to get rid of. Okay, so here's the kind of iterative scientific discovery process that I'm going to talk about as the context for this presentation. Let's say we start the loop with some data about something that we are interested in, maybe the properties of different molecules, and we're trying to discover molecules that will do a better job. So the first thing we do with that data is somehow we're going to model it, analyze it, and we can use, of course, machine learning for that. But an important part of this analysis, I will argue, is to generate multiple explanatory hypotheses. One way to think about this is we want a full Bayesian posterior over the possible explanations for that data. Now, having access to this model, including all of the uncertainty, ambiguity around it, we want to use maybe a different kind of machine learning. It's more like reinforcement learning, if you want, or bandits, in order to design the next round of experiments. So this is experimental design. The goal of that design is to maybe test these hypotheses or search in the space of hypotheses. So a hypothesis could be something like what is the causal structure of how genes interact with each other, or it could be this is a set of molecules that would be a cure for this drug. So these are the kinds of concrete questions that we may want to use these machine learning tools for that. Of course, once we have this batch of candidate hypotheses, then we go through experimentation, and that will give us more data. Now, as a special case, the experimentation actually doesn't have to be real experimentation. Sometimes you have cheap experimentation in the sense that you can run simulations, physical simulations, chemical simulations, or in biology, you can do experiments that are not the real thing. Like in vitro experiments is not the same thing as in vivo, but it might be a good proxy that's cheap, so we can do a lot of experiments. So that's a kind of setup where I'd like to propose machine learning methods. Now, if you're from these kinds of experimental sciences, physics, chemistry, biology, and others, one issue is, a good thing is we now are able to perform lots and lots of experiments, high throughput screening, do lots of experiments in parallel, measure very high dimensional things like the expression of genes and cells and so on. And there's just too much data for a single human brain to digest. And that's in addition to making sense of the whole literature that exists in your field with lots and lots of other experimental results. So we need machine learning, I think, to help us with that. And one of the aspects I'll be focusing on is think of this kind of scientific discovery problem as a search problem. And really, it's a hard search problem, like searching a needle in a haystack, where the size of the search space is exponential. So, the number of peptides, which is pretty small proteins of length less than 50 or something, is already 10 to the 60, and the number for full proteins is 10 to the several hundred. And that's not to speak of the space of different theories we could have to explain how they behave. These are just huge spaces. Another characteristic of these spaces is that we're not generally interested in a single good answer, but ideally we'd like to get all the good ones, and I'll explain why. So this is why I'm leaning towards methods like approximate posteriors, either over theories or over candidate solutions to the problem. Yeah, so there's a long history in active learning, Bayesian optimization, where we're setting the goal as an optimization problem. And I'd like to argue that really we want to do something more like exploration. So that's what I said. We want to produce a diversity of solutions, a diversity of samples that cover all the different ways, ideally, that we can solve the problem. So why do we care about this? In the case of scientific models, well, it's obvious, right? If there is two theories that explain the data, it's not enough to say, oh, I found a theory that explains it and this is it, and we can like just use it. It's important to know that maybe there are two different theories and they disagree in some ways. Because yeah, that's sort of obvious. And in the case of searching for things like drugs or new materials, it is also important because some of the solutions we may have proposed may look good according to our oracle, the black box. Let me show the black box that gives us an answer, but that oracle is not the final word. So, for example, in drug discovery, we might do in silico screenings, like trying to use chemistry and physics to decide whether a solution is good. But then those that seem to work well according to that criterion, we want to test in vitro screening. That's like single cell experiments or something like this. And for those that work, then we want to try animals. And then for those that work, we want to try humans, right? So you can see there's this hierarchy of gradually more expensive oracles, and the frontline oracles are just wrong. I mean, they're not the right thing. And so if you put all your eggs in the same basket, and I'll focus on like one solution that may look good according to the frontline oracle, then you may be in for bad surprises. What you want is to have an ensemble of solutions that are diverse, so that if half of them die, because in the next stage they don't actually work, maybe they're toxic drugs, then you still have the other ones. So that's the idea. Right. So we want to do something more like black box exploration for scientific discovery. So we still have this notion of oracle, but a sort of a greedy way to understand what we want to do now is, instead of maximizing, we want to find the values of the input X, think of a molecule, for which the function F, which may be our frontline oracle, is large. And a way to do that approximately is to sample from the modes of that function, or to find the modes of that function. And there's some relation to Thompson sampling, which is a method in Bandits. The idea is, if you're not sure what the right answer is for all kinds of reason, well, you want to sample your beliefs, so any of the modes, and then if your belief is correct, then you act according to that. In other words, you pick that molecule. But really, there's this idea of sampling from all the possibly good solutions according to your belief. Okay, so there's another problem. In classical methods in active learning and Bayesian optimization, we're going to cook up some kind of scoring function, what we call an acquisition function, say, that tells us whether a molecule is interesting or not, or a hypothesis is interesting or not. And then we're going to try all the possible solutions, compute the score for all of them. So it's in silico, it's something we can do in the computer, but if the number of possible solutions is 10 to the 60, then we can't do that. It made sense in the context of like original active learning, where people were using these methods to decide which example from an existing set of images should be labeled by humans. The list of examples is small. Maybe there's a million of them, but we can call neural net a million times. This is no big deal. We cannot call a neural net 10 to the 60 times or 10 to 300 times. So we need to find another solution. And the kind of solution that my group is exploring is one where we use generative models, or if you want a generative policy that samples solutions, ideally, from the modes of that scoring function that I talked about, the acquisition function. So the work that I'm proposing is kind of at the intersection of generative modeling, reinforcement learning, active learning, of course, and Bayesian methods. Okay. What is the quantity that we'd like to sample against, like to optimize if we were doing optimization? So I talked about these acquisition functions that people use in Bayesian optimization. In general, what we want is some kind of information gain. So how many bits of information about the quantities that I care about can I hope in expectation to get from an experiment? And that itself is not easy to compute, but we can use all kinds of approximations of that. Okay, so to recap the sort of auto loop here that we're looking at is illustrated here. So we have an oracle, maybe it's our in vitro experiments. We have a machine learning system. The machine learning system is going to propose a batch of candidate solutions to the problem we care about. And then, so think of them as a bunch of inputs, X, and then we're going to get a bunch of answers, which may be noisy, biased for all kinds of reasons, because it's a frontline oracle. But anyways, so we get these data points, X, Y pairs. And so we're going to use that as a augmented data set to train our machine learning system to propose a new batch. So that's the big loop, and we're going to focus on what we put in this little brain in the middle. But before I do that, let me say a few words about Aleatoric and Epistemic Uncertainty, which are important quantities involved in active learning. So if you look at the prediction errors that a system would make, like predicting Y given X in my previous slide, where does the error come from? And there are two really very different kinds of errors. There's the error due to the fact that there is noise in the data. It's what we call irreducible error. Even if you had the best possible model in the world, even if you had trained with infinite amount of data with infinite compute, you would still make some errors. Okay, so that's aleatoric uncertainty. And then there is the other source of error, which is due to the fact that we have a finite amount of data, essentially, and potentially finite amount of compute resources. So that's epistemic uncertainty. So epistemic comes from Greek and has to do with knowledge. So it's the uncertainty due to the lack of knowledge. And that knowledge can be improved, so the uncertainty can be reduced with more data, more compute, and so on. Now, when we do active learning, it's really epistemic uncertainty that we would like to reduce, because the other kind is not reducible. So the reason this is important is, imagine you can do an experiment where actually there will be a lot of noise, a lot of randomness in the outcomes, and so the uncertainty is high. But if that experiment is doesn't tell me anything about what I care about, because it's pure noise, for example, then, well, it's not an experiment I want to do, even though that entropy here is high. So it's only this part of entropy due to lack of knowledge, epistemic uncertainty, that we want to reduce in our experiments. Okay. Now there's an interesting category that I don't think people have been thinking too much about, is in between aleatoric uncertainty and epistemic uncertainty. So think about a completely deterministic system, like the physics is deterministic, let's say, of that system and your experimental system, but it's chaotic. So because it's deterministic, there is no noise, right? So you could think that your model of that system, its error is only due to epistemic uncertainty. And in a sense it is, but is it really reducible, right? In other words, if I do more experiments with that chaotic system, am I going to be able to improve my model? And well, in many cases, no. So there is like practically irreducible epistemic uncertainty that really fits more into the aleatoric uncertainty bin, in the sense that this is not something we care too much about. What we want is to do experiments that will improve our model in the sense of the ambiguity that it has about what the answers should be. Okay, so how do we kind of capture epistemic uncertainty? And there's a rich literature in machine learning. Many methods have been proposed. So they all, well, actually not all, but most of them go about this by thinking of, instead of training one predictor that gives you the one answer, you have, in some sense, a bunch of different predictions that could be compatible with the data. So you could use a Bayesian approach, for example, Bayesian neural nets, things like that, or Gaussian processes, where you think of the uncertainty really being encapsulated by your lack of certainty about what the parameters of the model should be. So you treat them as random variables. And typical epistemic uncertainty in this case would be, well, actually, it's not what I wrote here. The total entropy would be that of P of Y given X given the data, but that includes also the aleatoric uncertainty. But it's fairly easy to also come up with a formula that really focuses on the epistemic part of it. For example, if you think about sampling multiple times with different choices of parameters and comparing how your answers differ from each other. In fact, this has given rise to a very simple heuristic approximation of these kinds of Bayesian approaches called deep ensembles. It's just train a bunch of neural nets with the same data, different random initialization, and maybe the data is going to be presented in different order to add a bit of randomness here. And then you just measure something like the variance of their answers, or something a bit more subtle, but some estimated measure of disagreement between those neural nets. And that will give you what you want. I mean, approximately. And in terms of benchmarks, they seem to work quite well, and of course they're fairly cheap, compared to other methods, and simple to instrument, so they're used quite a bit. Okay, so let's step back a little bit on sort of the big picture of how we'd like to do this. Let me explain the different actors here. So on the right-hand side, the real world or your experimental bench, and for now, I'm just ignoring the fact that there are multiple oracles of different qualities. This is an interesting research direction in itself, and there's already some literature on this. But let's say you were able to measure what you care about. And so we have the data we have already acquired from the real world. From that, we train a world model. And the world model also has ambiguity. So we have some Bayesian uncertainty or epistemic uncertainty or something. In using both the predictions of the world model and the uncertainty around those predictions, we can come up with a reward for a policy that is the guy on the left, girl on the left, sorry, who imagines what the next experiment should be. And so once this policy is trained, we can use it to generate as a sampling exercise from its generative policy, generate candidate experiments, which you can think of actions in a model-based reinforcement learning setup. So this is very much like a model-based reinforcement learning setup. How do we train that policy in the model-based RL setup? We don't actually train it directly on the data. We train it to be compatible with the model, because we can query the model much faster than we can do experiments. So, doing things in your mind is cheaper than doing them in the real world. And once the policy is trained to be compatible with the model, including its uncertainty, then we can act in the world, because we have kind of converted our world model, which is like a joint distribution of things that you measure in your experiments, into a policy that is trying to find, for example, the sample experiments with probability proportional to how many bits of information they might give you in average. Okay, so this is the sort of high-level plan. Now I'm going to dive a little bit deeper and talk about how we may train this generative policy that I was talking about. So, and I suggested as a heuristic, we can train it to sample descriptions of experiments, let's call them X here, with the goal that it will sample those candidate experiments with probability here, PT, proportional to a reward function. So the reward function might be something like the number of bits I expect, or an approximation of the number of bits of information, of useful information I expect to get from the experiment. Okay, so this is a problem that you might have heard about before. Somebody gives you an unnormalized probability function and you'd like to build a generative model, or you'd like to sample from that distribution. And so you could use Monte Carlo Markov chain methods for this. Now, the problem with the MCMC methods is, I mean, they're like the standard ways of doing this, but they have issues. And in particular, remember, we are really interested in a case where the reward function has many modes. And if these modes are highly separated from each other, like very different kinds of solutions, MCMC methods may struggle a bit. And in fact, they may not give us what we want. They may get stuck in some of the modes, and asymptotically with infinite compute, they might give us all the modes, or even just a reasonable number. But there's the mode mixing issue. I don't know if I have a slide on this. Yes, I have. I'm going to explain what's going on with MCMC methods, which is problematic. If you're looking for sampling from a distribution with many modes, so here, typically in the MCMC world, we'll talk about energy function, which is just the minus log probability up to a constant. So we don't need to specify the partition function, but we want to sample from the corresponding distribution, like proportional to e to the minus energy. So what happens is MCMC methods, they proceed by small stochastic steps, by changing one possible solution by a small random move, and accepting those moves if they improve, or otherwise, accepting them with some probability. And that's nice to explore locally around a mode, and maybe to jump from one mode to another one that's very close, like in the picture at the bottom. But if the modes are very far and separated from each other, like on the top right, then it might take an exponential number of steps, of time steps, before it finds a path to another of these modes. So what can we do? Well, if you think about the process of what's going on in MCMC methods, you may realize that we're leaving a lot of money on the table. as a machine learning researcher, think about this. We have seen some configurations that gave us a high value of the function we care about, the reward function, like e to the minus energy. We've seen configurations which didn't work. So you can think of this as something related to a regression problem. And given the configurations that our chain has visited that were good and those that were not good, what would be other configurations that are good? And if we can generalize to guess what other configurations are good, then we could sample those configurations, go directly to modes that are good. For example, in the top right part, you see that we have visited these 3 modes and they happen to be lined up in this grid. So a good machine learning algorithm might see this and see, oh, maybe there's another mode there at the intersection that is shown there. And then they would try this. So the problem in high dimension is there are too many places to try. So you want a very smart method to try these other places. And MCMC methods mostly just try to do this by hand using domain knowledge that people have. Whereas if we use machine learning, we can train something like a generative model or policy that samples solutions and is rewarded for sampling good solutions. So that's exactly what would be amortized methods for doing the job of MCMC methods. So GFlowNets and some variational methods could be used for this in principle. There are some issues with variational methods, but so we had a first paper on these GFlowNets. So GFlowNets stands for Generative Flow Networks. The first paper was at NeurIPS last December. I'm going to read the title, Flow Network-Based Generative Models for Non-Iterative Diverse Candidate Generation. So let me unpack this a little bit. So the diverse candidate generation I talked about already. We want to get as many modes as possible of that unknown distribution for which we have an unnormalized function we can call the reward function that tells us, given a candidate, how good we think it is. Non-iterative here refers to the fact that unlike MCMC methods, we're going to generate a candidate in one shot. I mean, as in we don't need to try to modify a candidate many times before we say, okay, we have a good one. And the flow network idea I'm going to explain soon. And obviously this is a generative model, okay. So we have another paper that came out just before NeurIPS called GFlowNet Foundations that is under review right now. And that covers a lot of the mathematical foundations if you're interested. So let me say a few words about that beast. I won't have time to go into the details, so I encourage you to look at the tutorial that I'll mention at the end of my presentation. I think of GFlowNets potentially as a Swiss Army knife of probabilistic modeling. What they can do, as I advertised, is learn to sample from a distribution given some unnormalized target density or reward function. And the sampling is going to happen in steps. So we're going to sample a compositional object like a graph, a list, or we're going to sample maybe a vector, but through multiple steps. That's really the power of GFlowNet. So if you're going to sample everything in parallel, like in one Gaussian or something, then that's not interesting. But if you're going to do this in multiple steps, this is where the methodology becomes interesting. For example, you can use GFlowNets to sample sets, where there are many ways you could describe a set, because you can describe the list of the elements in any order. So this is something GFlowNets can do that is non-trivial for, say, RL methods that exist that might otherwise behave similarly. So you can sample in a non-autoregressive way. You don't have to know ahead of time what is a good order for constructing your object. Also, GFlowNets are not just samplers. They learn these, or they can learn these flow functions that are in the title. And these flow functions that I'll explain a bit more, they correspond to marginalized quantities. So marginalization means, we sum over a bunch of things. over the values of a bunch of things. And in general, marginalization is intractable or very expensive. And so these flows are going to be approximate flows, and they're going to be like neural nets that approximate these marginalized quantities that we care about. Okay, so let's take a fairly more concrete example. So let's say we want to use a GFlowNet to sample a graph, for example, the graph of a molecule that might be a candidate. So we're not going to generate the molecule just, out of nothing. We're going to do it in steps. That's what I said. In GFlowNets, generate through a sequence of steps. But the number of steps is not infinite, like in MCMC, where it's only asymptotically that you know that you have a good solution. Number of steps is going to be finite. For example, the size of the graph that we want to generate. So let's say at each step we add a new edge to the graph. So we devise a policy that takes the current graph, which may be the partial solution, and selects some action that will grow the graph to a bigger one, or chooses a special action that says, that's it, we're done, we have a good solution. So you can think of this as a neural net. Maybe it's a graph neural net, because here we take graphs as the objects as input, and the output might be a softmax over the actions that you can take. For example, choose a new node that could be added and decide where it should be connected. Okay, so what we're going to do with the GFlowNet is going to learn that policy. We might learn other things, but the most important thing we're going to learn with the GFlowNet is that policy that makes the transition from a state to the next state in this chain of transitions, where after a point we have the object that we care about. Okay, and now let me explain the flow story. So what we could do, remember, we're going to generate an object through a sequence of steps. We can think of all the trajectories to construct one of these objects. So the objects here may be graphs. So let's say that here in the figure on the right, the square nodes correspond to completed object, like a graph that we are happy with and that we're going to deliver as a candidate for some experiment, say. And the circles correspond to intermediate graphs, like graphs that we're still kind of constructing and maybe not finished. The edges correspond to transitions. So from the graph S3, I could maybe add a particular edge and I get a new graph S7, or I add another edge and decide this is the end, and I'm happy with that construction, and I get X3. So what about the blue things? Well, that's the flow. So imagine you were to construct a graph like this is a DAG, directly acyclic graph, which contains all of the possible ways you can construct all of the possible objects. And let's say for simplification, we start from a single state, like empty graph. And then, from that empty graph, you have a number of possible actions. Here, you can go to S1 or S2. Maybe you add this node or that node, and so on. And you see that it's a DAG, it's not a tree, because you have many different trajectories that could lead to the same graph. In general, this is true of graphs, but this is true of sets and many other ways to construct objects.
I have a question.
Yes.
So tying this slide into your previous slide, are the leaf nodes here taking an action to add another molecule, add another atom rather to the molecule, or are the leaf nodes saying, I'm done constructing the molecule, now let's test this drug?
Yes, it's the latter. So actually, I made a mistake when I said add an edge here. Really, the action here is this T symbol. It means terminal. We're done. And basically, we were happy with the graph we had in S3, and we just have this action that says, now let's hand that to the experimenters and get a reward.
So the policy in the previous slide is for deciding when you're done constructing the molecule? Or is
the
it
policy is for everything. So
yeah,
the policy is for every possible action. So maybe add an edge or stop. Everywhere in this graph, in this DAG, you have states where you apply the policy to decide what to do next, which could be to continue adding stuff or to stop.
Okay.
Does it make sense?
Yes.
I see two more people raise their hand. I'm happy to answer other questions. It's a good place.
It makes sense. Thank you.
Anything else?
Not for me.
Yeah. I was just wondering, how would you know when you should add an edge, or when the graph or molecule is complete, or when you need to add more edge? Like, how do you decide that? And how do you decide when to stop? Like,
that's what you learn. So that's why
Okay.
we're going to learn a policy that does that. So this neural net is going to have outputs that correspond to the possible actions, like add this edge or add that edge or stop. And so you're going to learn that neural net. You're going to train that neural net, and it's going to give you the policy that takes those decisions. That's the point of training here, is to figure out what the policy should be. Good. Anything else? I see more hands being raised, so let's do that. Oh, there's a question. How do you decide when the graph? Oh, okay.
I do have a quick follow-up. No.
Yeah, go ahead.
Yeah, so in the previous slide, you said that the policy could be a softmax, but I thought the policy was based entirely off of these flow equalizing equations. So
wait,
why are you saying the policy is a softmax if it's based entirely on the flows of your possible actions?
I'm going to explain that next. So there's a relationship between the flows and the policy, which I haven't described yet. But actually, so you have an equation at the bottom here which shows the relationship. So okay, I'm going to explain the notion of flows a bit more. So the flow is like the unnormalized probability of going through an edge or a node. So you see the equation at the bottom says the transition probability to go from state S to state S prime is just the flow for that edge normalized over all the flows of the outgoing edges from node S. So the flows are just unnormalized probabilities. And the reason we call them flows is because, think of the water here, think of a big pipeline, right? With all these pipes and T's, and where, the water can come back to, like it is in the figure here. So the water flows through these, and then you have nodes like S3 where you've got incoming water from both S1 and S2, but also outgoing, into S7 or X3. And there will be some flow constraints here that, like, the amount of water coming into S3 should be equal to the amount of water coming out of S3. And we're going to use those constraints to define kind of the semantics of this whole thing, and also define what the transition probabilities should be. So we're going to relate the flows that are like these probabilities of visiting. They're like visiting probabilities for edges and nodes. You can have a flow for a node, and you have a flow for an edge, they're related with each other. So the first relationship is the policy that we're going to learn is directly connected to the flow function on the edges by normalization. So that's one thing. Let me show you, so then there is a theorem which is very important, which is saying that somehow if you can learn a flow function that satisfies the flow constraint that I just said, like the incoming flow into a node, into a state is equal to the outgoing flow from that state, then you just have to follow the policy that uses these edge flows to sample, and you're going to get on the terminal nodes, you're going to get samples visiting those terminal nodes with probability that you want, that is proportional to the reward in those edges. So there's a constraint here I forgot to just explain. We're going to set the reward to be equal to the flow into the terminal nodes. So we know with what unnormalized probability we'd like to get X3. So we're going to set the flow function for X3 to be equal to that reward. Okay, so in other words, we know how much these are, like, that's the red edges because they're special. We know the flow for them. What we're trying to get are the flows for all the other edges. Of course, there's an exponential number of them, so we can't enumerate all of them. It's just a figure for illustration. In the real world, we're going to have functions, like not table lookup, but neural nets that tell us the flows everywhere. But of course, it's going to be an approximation, and so the theorem says if you just manage to get those flows matched, and of course that you get the right flows on the terminal edges. I mean, this is how you define the flow coming out of S3 here, that it has these constant rather than the neural net output. Then you're done. And you got a bonus, which is you can read from the flow in the initial state the partition function of that normalized probability function, which is just sum over all the terminals of the rewards in those terminals. And if you just, you can just look at the figure here, and it's pretty obvious that the amount of water coming out of S0 must be equal to the total water flowing out of, getting into all the terminal edges or terminal states, right? So this is a proof by inspection, but there's real math behind it. Okay, so that's one important result. Now, since we wrote the first paper, we came up with a bunch of different ways of training GFlowNets, and they all correspond to different ways of getting those constraints with various properties that I want to have time to talk about. But the typical one we use these days is in the bottom here, where we don't even need the edge flows explicitly. We just need to parameterize the forward transition, but we also need to parameterize the backward transition in this formulation. That is just similar to the forward, except we normalize over the backward edges, going back to the previous state. And so what it means is that if you give me a particular trajectory, a particular way of constructing an answer. So if I have a particular trajectory that starts at S0 and ends up, let's say, at X3, I can use these objectives to score how good it is, in the sense that if we can make those losses zero and they're positive everywhere, meaning for all trajectories, then we get what we want. Now, of course, we'll never be able to visit all the trajectories, but this is a machine learning problem. And we will be hopefully able to generalize if there is something to be generalized. By the way, this connects to this slide, which is, when would there be an advantage to MCMC methods compared to, amortized methods like variational methods or GFlowNets compared to MCMC methods? Well, that's if it is possible to generalize, given the modes you have already visited, like the trajectories that you visited and how good they were, like what reward you got. Can you generalize to guess reasonably well in other places? Of course, the more trajectories you will sample and train on, the better the system will get. But you'd like the training of GFlowNets to be as quick as possible. So if there is statistical structure or something like this that allows generalization, then these amortized methods will work better than MCMC. All right. Okay, I'm going to skip a few things. So there's a number of other papers, like this one that explains one of the training objectives I mentioned, trajectory balance. This one, which explains how you can learn the reward function using a maximum likelihood approximation called contrastive divergence. This one, which applies the GFlowNets in a active learning setting of designing biological sequences like peptides. And I'm going to skip these because I'd like to tell you a little bit about the part that is not active learning, that is not really like the experimental design part, but I'd like to tell you a few words about the causality part that I promised at the beginning. So I have a conjecture that when there are several causal explanations, like in other words, several models that maybe causal models, meaning where you identify variables as causes and effects and how they're related to each other, which is cause of what, and so on. The conjecture is that the Bayesian posterior, given the data over all these models, is the best you can do in terms of extracting information from that data. You have to connect that with the literature on causality, where people ask a different question, which is the identifiability question. So the identifiability question is, if I had infinite amount of data, would I be able to fully answer particular questions in a non-ambiguous way? Like, what is the graph? What is the causal graph that relates these variables, or some more specific question about some of these variables? And in general, lots of models you can think of are not identifiable. In other words, they're even with infinite data. That's one of the interesting aspects of causality. There may be still ambiguity about which models explain the data. Now, what I like about the Bayesian posterior is that in the limit of infinite data, it still gives you the answer to, well, is it identifiable? And even better than that, what's called the equivalence class of all the models that are compatible with the data. But it also works with finite data, which is what we have in reality. And it will give us the ambiguity or the uncertainty due to both the fact that there are like intrinsically difficult ambiguities, that's the identifiability, but also ambiguities due to finite data. Okay, so that's a motivation. I'm going to skip the, well, this one thing I'm going to quickly say is that if you had a good Bayesian posterior over the causal models that explain your data, then you could calculate, and especially if you use machine learning and neural nets and stuff to amortize the calculation, you could calculate, you could estimate the information gain that I talked about at the beginning. So the information gain is something like the mutual information between the outcomes of an experiment that you could do, you haven't done yet, and the model that you currently have, in the sense of as a random variable, because you don't know what is the right model. But given the data, you have a distribution over models, so that's like a random variable. But there's another random variable, which is the outcome of an experiment. And you'd like to know how many bits in common these two random variables are, and that is the information gain about your model. You could also have the mutual information with a specific question that your model allows to answer. And typically, in many applications, we might not be interested in knowing everything, but just the answer to some questions of interest. But that can also be framed with this mutual information. And if you had the posterior, then you would have these sums or integrals that are intractable to compute these information gains. But again, you can use the same kinds of tricks that I've talked about with flows or other machine learning methods to train neural nets to approximate these marginalized quantities. And then you can use those neural nets as reward functions for training the policy, like the GFlowNet policy that I talked about, that will generate candidate experiments. So you really have to go back to this big picture here. So the Bayesian posterior I'm talking about is the world model. And then this can allow us to estimate things like mutual information between a candidate experiment, like an imagined experiment, and things we care about. That becomes a reward for training our GFlowNet that will, once it's trained, give us samples that correspond to experiments that would give us a high information gain. Okay, so we've started doing this sort of thing. On the Bayesian side of things, with Bayesian posteriors, we have a first paper that uses GFlowNets to sample from the causal graph, but it's in a very simple setting where all the variables are observed. and also the mechanisms are simple in the sense that everything is discrete and low dimensional, so we can use analytic methods to compute the posterior on the parameters of the mechanisms. I know I'm probably using terms that most people don't understand, so I think I'm going to stop soon to allow for more questions. There is a tutorial that I wrote and with my collaborators called GFlowNet tutorial on tiny URL. I'll paste that in the chat while I'm answering questions.
Yes, so thank you very much. I have two questions. I'm not sure that I understood the flow model, so I have two questions about the flow model. So
it takes a while.
Yeah, thank you. So it looks like you generated like a Thompson sampling on each of the edge. Like, so when I get to like a vertex,
no.
Like...
So the connection to Thompson sampling is more like at a high level, abstract level, in the sense that if you think about the different hypotheses, different beliefs that you may have, say for drug discovery, is this molecule is going to cure disease, or this one is going to cure the disease. These are hypotheses. When you use Thompson sampling, what the recipe is, sample from your beliefs and then act optimally according to that belief. So if I believe that this is the right molecule, then I'm just going to use that molecule as a candidate, but you're going to do that many times. So Thompson sampling says, okay, go and keep sampling from your beliefs to choose the optimal action. And in a way, GFlowNets are doing something very similar, because we're sampling from the posterior, and that's sort of your belief as well. Yeah, but in a sense, you created now like a random graph, like that. It looks like what the flow does, it's a random walk that you optimize. Absolutely. Yeah, we have a generative model, so it goes through a sequence of actions, and the graph that you generate, if it's a graph that's the object of interest, is going to be a random graph, because we have distribution of graphs now. Yes. And the second thing is, it looks like once I go to a state, for example, if the states are to either add a molecule to my drug or then to add and verify. So it looks like in a way you only have a memory of fun, right? Because I only care like what was my previous vertex on the random graph. Oh, no. Here, a node in the graph. Okay, so because there are two graphs and people got confused, that's my fault. So there's the graph that corresponds to the molecule that I'm building. And we're going to grow that graph. And there's the other graph that shows all the ways that I can do that, where each node is a graph. So I can construct a graph in a sequence of steps where I add edges. So that forms a trajectory in this DAG that I showed, where the water was flowing. And so each node there is a full graph. So when I add the next edge, this is conditioned on the graph that I've already constructed. I mean, partially constructed. Initially it's empty, and then it has maybe one edge and then two edges and so on. So it's always conditioned on the full state. It's called the state because it has all the information that I need to take the next action. Okay. Now I got it. Thank you very much. You're welcome.
I have a question. So you framed a lot of your talk in terms of exploring hypothesis space for scientific discovery. And I think the same framework can apply equally well to decision-making processes that humans perform every day. And so I'd like to ask you about using this framework to model and solve meta MDPs as a way of understanding everyday decision making and internal thought. So yeah, so like in my research, we use meta MDPs to describe resource rational decision making, where people make these internal mental computations to transition to new belief states. And the resource rational objective is to trade off the cost of that thinking with the expected utility of the resultant action in the external world. And so, of course, the resultant action in the external world is the leaf state in the GFlowNet. And one of the big challenges for solving these meta MDPs is credit assignment, because the reward doesn't come until after you've done all this thinking. And the GFlowNets seem appropriate for representing this, because there's this efficient propagation of credit and reward. And the DAG structure in particular is very appropriate for this kind of compositional thought process where multiple trajectories can get you into the same belief state. So you're not wasting these samples on redundant kind of sequences of thought. And so I'm wondering if you've thought about using GFlowNets like to solve meta MDPs, and since those are a bit niche, more generally POMDPs, because a meta MDP is just kind of a special case of a POMDP. And number two, like I know you've stated your interest in using them to understand internal thought applied to external actions, but I would like to hear you talk more specifically about what you've thought about that and how you've thought about approaching that.
Okay, that's a whole other talk, but yes. Let me, I mean, pretty much everything you said makes sense to me. There's an interesting fact that people don't necessarily like have satisfying theories for, which is animals and humans act in a way that seems irrational sometimes, in the sense that if there are different options, we don't go for the most valuable one. We seem to sample proportionally to the reward that we will get. And rats do that, humans do that, and it's kind of weird. It's not. It seems that it's not rational. But if you think about what I've talked about today, it may be rational. So if for some reason there's uncertainty in the reward that you'll get, or there will be subsequent steps, or you think that another kind of explanation is that it's not just like this one human trying something. We have a whole population of humans. So there's this argument that we should visit all the possible resources or places where we can get reward collectively, right? And then the optimal thing to do is for individuals to sample like in a Thompson sampling kind of way, where we don't go for the optimal thing, but we follow our belief and sample that belief and then act optimally according to that. Anyways, so that's sort of interesting connection. Yes, I'm thinking of GFlowNets for thinking, like as modeling system 2 thought processes. In fact, if you think about the graph that I talked about, it could be a thought. The nodes could correspond to things like words or concepts, and the edges correspond to relations between them. Think about the parse of a tree of a sentence is really a graph. And it's all actions, unlike like the typical way we think about RL. These actions are internal actions, as you noted. They're not things you do in the real world. They're things that are computations in order to come up with some external action. So they have different properties and we can exploit them. Regarding the credit assignment, the reason we have been exploring, one of the reasons we've been exploring different objective functions to train GFlowNets is because we suspect that on longer sequences, so when you have many actions to define an answer to a question, the original one in the NeurIPS paper doesn't fare as well. And it's a credit assignment thing similar to what you have in RL, because it uses something similar to Bellman equation in a way, where the flow function is kind of similar to value function in RL. It's not the same, but it has a similar flavor. The trajectory, so what it means is that credit assignment will trickle through the updates of the flow function if you have a long sequence, just like value function makes reward trickle to early actions. Whereas the trajectory balance and others in its family that we have been working on will get a gradient signal on all the actions in the sequence. So in a sense, they're a little bit more like policy gradient in RL. It's not the same either, but there's some connection. So this is a whole like interesting question of how do we get the best of both worlds, fast credit assignment and low variance also in the gradients, which is similar to some of the questions people ask in RL.
All right, so I guess if there are no more questions, let's give another round of applause to Professor Bengio for a very interesting and informative talk.
My pleasure. Thank you very much. Thanks for your questions. Bye-bye. And if people have interest in this, like, don't hesitate to write to me. Bye.